good. Well, let's start the evening session. I'm happy to introduce Qian Yin, who will talk about Lattes maps and combinatorial expansion.
Hello? Can you hear me? Okay.
No, can't hear you. Louder.
Hello? So Curtis McMullen said the following, which I can't agree with more. He said, have two advisors, like have a wife and a mistress. And in my case, it's kind of clear who's the wife and who's the mistress. Whenever I go visit Dennis, he's talking about really fun and great ideas. And then I come back to Mario, and he wouldn't believe a word I said unless I do the work, i.e., write everything up carefully with all the details. So I just want to use this chance to thank Dennis for sharing his mathematical wisdom and enthusiasm. Oh, well, I better shut up and get back to work since my wife is staring at me seriously. So in 1918, Samuel Latte wrote a very brief, interesting paper describing an extremely interesting class of rational maps. Even though similar rational map examples has been started by Schroeder 50 years earlier, but Latte's name has been firmly attached to this class of maps. So now we call it a Lattes map. And let's see what's a Lattes map. So Lattes map is a rational map obtained from a finite quotient of torus endomorphism. We couldn't satisfy the following commutative diagram, where T is a torus, A bar is a quotient of a fine map of the complex plane, and theta is a finite to one holomorphic map. For example, theta can be think of as a Weierstrass P function. Latte maps play exceptional role play a role as exceptional examples in complex dynamic literature, and there's some properties. That's why it's so special. And first is the first examples of Julia set are the whole complex plane. Second is the post-critical set is finite. Recall the definition of post-critical set. It's the forward orbit of critical points of F. And Latte's map corresponds to, so Thurston assign an orbifold to all the Thurston maps, and the Latte's map corresponds to the parabolic orbifolds, which its characteristic class is equal to 0. And sorry? Yeah, OI characteristic is equal to 0. I thought you were text message. And it's the only rational maps whose measure of maximal entropy is absolutely continuous with respect to the Lebesgue measure. And this conjecture already mentioned in Dick Canary's talk, which the significance of this conjecture showed by Hamenstadt and Sullivan that if the conjecture is true, then the hyperbolicity is dense among all the rational maps. Okay, let's review some definitions in Mario Bunk's talk on Tuesday. So Thurston defined the Thurston map with just a branch covering, which means locally looks like Z to the, after coordinate change, locally look like Z to the D. and with finite post-critical set. And yeah, yes, for some D. It is called expanding if there exists a Jordan curve which contains the post-critical set and satisfy this lame mesh thing, which equals to 0, and this lame mesh is the think of you on your sphere, you take off the Jordan curve passing on the post-critical set, and you keep on pulling it back. And if the diameter goes to 0 when n goes to infinity uniformly, then this is called expanding. Another way to think of this is just take any Jordan curve, open a Jordan curve, not containing the post-critical set, and you pull it back, and uniformly, the diameter goes to 0 uniformly when n goes to infinity. And here the metric, just any metric, as long as it's induced the standard topology, and if it's expanding for one Jordan curve, then the expanding property doesn't depend on the Jordan curve you choose, as long as the Jordan curve passing all the post-critical set. And Mario mentioned in his talk that a rational map is expanding Thurston map if and only if there's no periodic critical points, if and only if the Julia set is the whole Riemann sphere. So Latte maps are examples of expanding Thurston maps. Okay, let's go to more pictures. So this example, this is topological to the spheres obtained by 2 copies of a unit square identified on the boundary. And so we map, so we color the front of the unit, we call this a payload. We color the front of the payload black and the back of the payload white. And so now we map, we divide this to 4 equal parts and map the black one to the front and then this one to the back, and do it in the same way for the back. And so locally, this is z to the z. Locally, this is z to the state square. And so for this map, the critical points are so the center of the front and the center of the back, and then the center of the edge. And so the post-critical set, actually it's these 4 points, because eventually this the center and the back and the center of each edge map to the 4 corners, and the 4 corners eventually map to 0. In Mario's talk, he also described another example, which is in the front of, along this edge, he stick which we call a thimble. So then locally that is like z to the cube. So that's also I have the same post-critical set, so it's also example of Thurston map. So before I tell you my main theorem, I need some more definitions. So I'm going to define a sequence of cell decompositions for a Thurston map and fixed Jordan curve. So the 0 level cell decomposition is so here the 0 means 0 level, and the 0 here. So we use the vertices, edges, the tiles to describe the dimension of the cells. So let the post-critical set of F to be the 0 vertices, and then let the Jordan curve C minus all the post-critical set. Let's draw. So let's think this is just the sphere. And so if I have a poster, this is the 0 vertices. And so these are just the 0 edges. And then the inside and outside are the 0 tiles. So we pull back all this cell decomposition. We're going to, by f to the inverse, we got the 1 vertices, 1 edges, and 1 tiles. So the 1 here corresponding to the 1 level doesn't mean the dimension. And we keep on doing this. So we get a sequence of cell decompositions. And so another way to say the map is Thurston map is expanding if the n cells, the diameter of the n cells go to 0 as n go to infinity. Questions so far?
Cells? What is the n tiles?
Oh yeah, n cells means can be n vertices, n edges, and all n tiles. Yeah. So cell is just homeomorphic to a closed disk. Depends on the dimension. Any other questions? Okay, now I define this dn to be the minimum number of n tiles needed to join two non-adjacent 0 edges. So, say if we have this is the 0 edges, and so our n tiles are much smaller. So if n tiles are like this, they are not joining the non-adjacent, so the n tiles have to join non-adjacent. So going to be looks like this. And the minimum of any of them, so which will be the dn. So the following inequality is always true for Thurston map without a periodic critical points. For any Thurston map without a periodic critical point.
Can you expand?
No, doesn't need to be expanding. So which means the growth of dn is controlled by the degree of f. And let's look at some examples. So this the example we talked before, just map the black to the front and the white to the back. And if you keep on iterating, you're going to, let's focus the front, let's look at the front of the pillow. So going to be looks like this. So, so this is the 0 level. Or we take take the Jordan curve to be the boundary of the unit square. And so you pull it back, so the boundary is going to be the grid of this pillow. And this is 1 level. And then you keep on pulling back. This is the second level. And the front of the pillow looks like this. And the black going to map to the black tile here, and the white map to the white. And you keep on pulling back by G, it's going to look like a checkboard. And so what's the dn? What's your guess for dn? So dn is the minimum number of n tiles joining non-adjacent edges. So the dn was 2 to the n, which equal to the degree of G. So this satisfies the inequality here. And let's look at another, sorry.
Could you show us the statement again?
Sorry, the theorem, okay. The proposition is there's a constant C such that the growth of dn is bounded by the degree of f.
How does dn depend on C?
dn depends on C?
Oh,
the Jordan curve, yes.
There are two different C's.
Two C's.
Oh, 2C, sorry, yeah. This C is the Jordan curve.
Yeah, great.
This C is a constant. Yeah.
So does the second C depend on the first C?
Sorry, say it again?
So does the second C depend on the first C?
Yeah, the second C definitely depends on the C, but for dn, depends on the first C, but dn have the following property that for different C, Jordan curve C, the ratio is bounded from above and from below. So for the same f and for different C, Jordan curve C, so it's bounded. Let's use you see? So which means the growth rate of the n doesn't depend on the Jordan curve C you choose. Okay. Excuse me. Sorry, had a bad allergies.
Is that more or less like, I'll make my question long so you can cover. Is that more or less like the proof that the length of a word in a group doesn't depend on the number, on the generated set? So you can rewrite
Yeah.
an old generator in terms of new generators.
For the n, sorry, is that?
For dn,
Yeah.
I like that proof. I mean, just rewrite one tile system in terms of another.
Yes, yes. You.
At the beginning stage, and then just pull it all back.
Yeah. Let's look at another example. So this one, I still color the front black, the payload, and the back white, and map the black and white accordingly. And so this is also the posterior critical set, still the 4 corner points. And so what's the degree of this map? You just pick a generic point and see how many pre-images. So the degree is 6. Okay, good. And so if you keep on pulling back, let's focus on the front of the payload. And so going to be looks like this. And this way, that's more and more tile this way. It looks the same as the example, looks similar as the previous example. So what's your guess for the n for this example? So the n is the minimum number of joining opposite sides. So for this one, it's still 2 to the n.
Yeah.
And so we get to the inequality 2 to the n. It's less than the degree. And so let's compare these two examples. And this one actually is an example of Lattes map, and the other, which is rational map, and the other one is never will be topologically conjugate to a rational map. And the difference of these two examples is this one, the growth of the dn is almost the same as the growth of the degree of g to the square root of degree of g. And so this actually, the amazing thing of this is it's actually characterize Lattes maps among Thurston maps by this growth rate. I mean, the way to think about it is Lattes maps is a rational map. So which means the way it's expanding from any angle must be the same. It's a conformal map. And this one, it's the expanding one is expanding 3 to the n, the other one is expanding 2 to the n, so there's no way it's a rational map. And so this is the main theorem. See, if S just given any topological map, and it's topologically conjugate to a Lattes map if the following conditions are held. Of course, it needs to be expanding Thurston and can't have a periodic critical points. And so the third condition is the other inequality.
Do you need all those conditions?
Yes, you do. It's if and only if. It's a bold face. It's bold.
I thought it might be if and only if the last thing. Also, I mean, the first and third. I mean, maybe it can't happen. I don't know. I was just wondering if it can happen. It looks like that if it was a periodic critical point, because then it wouldn't feel, it wouldn't be full somehow.
Thanks for the question. Okay, so I'm going to give a sketch of the proof of this theorem. So the hardest part of the proof is to show there exists a visual metric on S2 with expansion factor degree f half. So a visual metric induced by Thurston map was introduced by Mario Banca and Daniel Meyer. And so it has a geometric characterization as the n tiles is roughly, let's see, a visual metric D with expansion factor lambda. It has geometric characterization is that for any n tiles, it's roughly have the size of lambda to the negative n. And for any two non-disjoint n tiles, the distance has to at least roughly lambda to the negative n. So,
So what do you deduce from that?
sorry?
What do you deduce from that argument?
Which argument? If there exists a visual,
tiles that are not adjacent, at least landed lines in apart.
which means if they can't be they can't be really close.
Yeah. I'm trying to talk, okay, I thought you were in the middle of an argument, so I was asking.
Oh, it's just the geometric characterization of the visual metric. I don't want to tell you the definition because it's too technical. So think about this metric, which give you each n tiles roughly this size, and two non-adjacent ones can't be too far apart, can't be too close. Thanks. And so once we have this, then the rest are follow from a couple big theorem. So if we get this visual metric, then by theorem of Bank and Meyer, that this space is alpha 2 regular in this metric. Recall alpha 2 regular was introduced. I think Bruce Kleiner talked about it. It means the host of 2 measure is so for all the for a ball with radius r, the host of 2 measure of is roughly r to the 2, have the size r to the 2. And if we know that, and then by Bank and Kleiner's theorem, which Mario mentioned in his talk, that if you have a space is homeomorphic to S2, and it's alpha 2 regular, and LLC, which is linear locally connected, which means you rule out the cusp. Think about that, and then this space is quasi-symmetric to the Riemann sphere, the standard Riemann sphere.
I thought there was one more hypothesis.
No. For this theorem? Sorry, which theorem?
Regular.
It's alpha 2 regular and LLC.
That implies quasi-symmetry.
It implies quasi. You can confirm with Mario.
I don't believe it. No.
And so if we knew that the space is quasi-symmetrically to the Riemann sphere, then by this theorem of Bank and Meyer, the space is quasi-symmetric to Riemann sphere, And if it also has a virometric, then this F is topologically conjugate to a rational map. So this is how the rational map come in. So once we had that our map F is topologically conjugated to a rational map, so now we can just focus on the rational map. And now our rational map also has a virometric, that's I'll still call it D, that with the expansion factor, degree of square root of degree F. And also our rational map has its alphas 2 regular with the induced metric. And also our rational map R, its induced metric is quasi-symmetric to the Riemann sphere. Anyway, once we know this, so for this rational map, by Juha and Pekka-Kuskler's theorem, they said if two spaces are locally if two Q regular spaces are locally compact, two locally compact Q regular space are quasi-symmetric to each other, and one of them satisfy a weak 1p Pongarian inequality, well, some technical inequality, which our Riemann sphere satisfy anyway. Then this the host of matter is induced by our metric is absolutely continuous with respect to the Lebesgue measure. So this basically tells you that our host of matter induced by this metric D is as good as the host of matter induced by the cordial metric on the Riemann sphere, which shows that R is a lattice map. Thank you.
Any questions for Qian? Sorry, any questions for Qian?
Well, I used the equivalent of Zudunic theorem. It's by Mayer, yeah, which conjectured by you, which I forgot to mention.
Your abstract mentioned the result of Hamenstadt. How does it work?
Actually, so that's a good question. They told me only 20 minutes, so I didn't prepare that. So this degree F is actually, I mean, I'm not sure, it's related to the topological entropy, which is the log of degree F for the map F. And this dn actually related to, what's it called, asymptotic upper curvature for a group of hyperbolic space, which is introduced by Mario and Fucher. So basically, this it's establish a relation of the entropy and the curvature. So that's how much this rigidity that it's established a relation of the curvature and the entropy. I can tell you more if you are interested later.
So if you take the examples where you're building with thimbles, sometimes that'll be conjugate to a rational map, and sometimes it won't, right?
Yes.
When it is, under which conditions is it going to be conjugate to a Lattes map? Do you know?
So what's the conditions?
Yeah.
Going to be? I think it's that, say, so let's say we have the grid. Well, I mean, if you only have the example we had here with one symbol, there's no way you can make it a latte. Let's have more grid, just map F to the front and this is front and the back of the payload. We can assume even have more. thimble on the horizontal way, and if you have equivalent, that's also the same number of thimble vertically. Somehow you like make the modulus sort of evened out in. Like you can think of sort of the growth. It's each direction sort of evened up, so sort of conform more. So in this case, like if you have a more thimble horizontally, then you need more thimble vertically. I think so.
And then all of those will actually be conjugate to a Lattes map?
I don't think this will conjugate to a Lattes map, but it's definitely conjugate to a rational map.
Right. Okay.
But
so do you know like when those would be conjugate actually to a Lattes map?
no,
Well, easier question, are any of those not conjugate to a lattice map or conjugate to a rational map?
sorry, I don't know the. I don't think I know the answer. I need to think about it.
Well, I think that if you are putting a small flux, then there is so-called substance abstractions, and you can count the degree and maybe you. No?
These are rational. These are conjugate to rational.
So if you.
If you only have one, then you get a Thurston abstraction. These are rational. These are conjugate to rational.
Rational map,
They're
but
certainly
not Latte map.
They're not Latte by your theorem.
Yeah, no, yes.
Why not? Why is your theorem satisfied?
dn is too small. dn grows
The
like
degree
dn,
is
but the
much
degree
bigger.
is higher.
What?
The degree is much bigger in this map.
Oh, I see.
That's the point. You can circumvent the flat. You don't have to go through them.
Oh, I see. You could sneak through. So the dn doesn't change.
Yeah, the dn doesn't change.
Sneak
Yeah.
through, but you change the degree.
The degree
Oh, it's
changes.
obvious. Okay.
Yeah. I mean, the degree of this map is huge already anyway.
So what are those maps? What are those rational maps?
Any other questions?
What are those Yeah. Yeah. Okay.
Yeah, it is expanding because if you're pulling back, getting smaller.
Why are they conformal? Why are they?
I don't want to tell you later.
Any other questions that she doesn't want to tell you later about? Maybe we should thank her again and take a 10-minute break.